Physics 2211, Lab 1, Shaswat Dhakal. Introduction, purpose. This is the constant velocity lab. This lab has two main components. The first component is to find an object in motion traveling at constant velocity, captured on video, and use tracker to observe its position as it travels in constant velocity. Collect data on the object to create a position versus time graph. Second component is for the same object traveling at the same constant velocity, create a computational model that will predict the object's position as it travels in constant velocity. Collect data from the computational model to create a predicted position versus time graph. The purpose of this lab is to compare the tracker analysis and the computational model to see how similar/different the results are, and to understand why these similarities and differences exist. Background knowledge. Newton's first law. If the net force acting on an object is zero, it will either stay at rest or stay in motion with the same velocity. Newton's second law. The final velocity equals the initial velocity plus the net force over mass times the change in time. Constant velocity. This occurs when the net force is zero. This means the object is moving at the same speed and direction. Change in position. The final position equals the initial position plus the average velocity times the change in time. Average velocity. The initial velocity plus the final velocity divided by 2. Experiment overview. The object I used for the experiment was a standard NHL hockey puck. I had my mom roll it on a table while I recorded the video. I used tracker to gather data on the puck's position at certain times. I obtained the position of the puck after 0.033 seconds passed for 0.933 seconds. The system is the puck and the surroundings are everything else that is around the puck. Computational model overview. To gather data for the computational model, I weighed my hockey puck and looked up the diameter of a standard NHL puck. I calculated the velocity of the puck by using the average velocity formula on the position points of the hockey puck at 0 seconds and 0.0033 seconds. Brief overview of the results. While the computational model had very similar results to the experiment at the beginning, as the experiment went on, the computational model overpredicted the position of the puck. Experiment. In tracker, I used the first quadrant of the Cartesian plane to graph my position versus time graph. Since the puck was traveling from left to right, I had the puck's initial position near the origin and it traveling in the positive x direction. This resulted in a positive slope. To get the location of the puck, I would click on where the center of the mass of the puck was in each video frame. Here's the video. Computational model. I used the start position in the model that I used in tracker. Line 35. I used the velocity by calculating the average velocity between 0 seconds and 0.33 seconds by using the data in tracker. This is at line 36, and you can see both of those right here. I updated the puck's velocity using Newton's second law in line 58, and that's right here. Because the net force is zero, the velocity of the puck never changes, and that happens at line 54. As you can see, the net force is the zero vector. I use the change in position formula to update the change in position of the puck, and that's at line 60 right here. And as you can see, I used a while loop, so this would happen while the time is 0 till the time is 0.933. Discussion. Comparison between the experiment and the computational model. At first, the computational model and the experiment show similar data. However, as time passes, the computational model tends to overpredict the location of the puck. This shows that the puck is not actually moving at constant velocity, thus the net force acting on the puck is actually not zero. This is likely due to the friction that is acting upon the puck, thus decreasing the velocity of the puck. Potential errors. Human errors using tracker. Because I had to manually locate the center of the mass of the puck in tracker, I might have been slightly off of where the actual center of mass was. This can affect the position of the puck. Human errors rolling the puck. When my mom rolled the puck, she did her best to ensure it was traveling in the same direction. While it appears to be traveling in the same direction and in a straight line, we do not know for 100% certainty that it is traveling in the straight line. This can affect the velocity of the puck. Additional questions. When you analyzed your video in tracker, you made a choice of the orientation of the puck, of the axis, Discuss briefly how your results would change if you were to flip the axes. So this would cause the slope to no longer be positive, the slope would become negative. However, the absolute value and the magnitude of the velocity and the position would remain the same. This would still allow me to obtain the exact same results. What does it mean? Your observations can be predicted well by your computational model when you set the net force equal to 0 in your model. Is it possible for you to say how many pushes and pulls are added together to give 0 net force in the case that you observe? Discuss briefly. No, it is not possible. This is because there are many forces to account for, such as air resistance, friction, and the force of rolling the puck. Without being able to account for all these forces, we cannot achieve a net force of 0 for our experiment. Conclusion. While the experiment and the computational model showed similar results at first, as time went on, the computational model overpredicted the position of the puck. This is due to the puck not having a net force of 0 in the experiment. Since the puck did not have a net force of 0 in the experiment, it was not in constant velocity, thus causing the computational model to not match the result of the experiments. Thank you for watching.